Welcome to Presentation 5.2, Introduction to Communication Networks. I'm your professor, Jacob Reidt. Let's go ahead and get started. In this presentation, we're going to be picking up where we left off in 5.1, specifically on the information networks that communications bridges the gaps on. We'll be taking a look at some of the use cases, some of the ownership strategies versus leasing strategies, the communication technologies that might be employed, and as well as some of the interoperability and security considerations that one has to apply when choosing a communications network. We'll then finally wrap up with a reference list and some required reading, as well as a segue into our discussion board conversations. As we discussed in the previous lecture, this NIST framework really provides a good summary of all the different operational domains as well as the interconnecting information networks that are needed in order to make system automation really work. Now, the framework for this class is that we're trying to equip you with the tools that would be necessary and the knowledge that would be necessary to be an introductory worker in the system automation domain. Now, as far as it comes to communication networks, what we're finding is that the topology and range of technologies for communications is so broad and so diverse, it's really becoming a concentrated specialty, and it isn't something that is often left to, say, the operational engineers or the transmission engineers or the distribution engineers, but rather is getting concentrated more specifically in communication groups, be they in traditional engineering operations or in infrastructure technology or information technology such as Avista is aligned. That being said, we will continue to try and give at least an overview of the communication networks such that you would be able to arm yourself with some introductory knowledge in that area. The architecture of the communication networks will really dictate a number of the performance characteristics with which you design them. For instance, on the internet, it's required that it be highly interoperable and highly routable due to the number of endpoints. So much so that an entirely separate protocol was developed, not ironically named the Internet Protocol, or IP. IP, of course, is a very prevalent technology and communication networks, both on back office systems, traditional IT systems, and is becoming more and more the ubiquitous standard for communication frameworks. Wide area networks are necessarily covering huge geographic areas, so you have to have technologies that can handle long haul transmission, and then there may be some ability for us to interoperate quite necessarily between more urban and more rural configurations that would necessitate maybe places where fiber optics would make sense, but maybe places where wireless communications would make sense. A local area network, on the other hand, is something that is very, very specific to maybe a particular building. And so the transmission media is going to be very specific and not highly integrated. And it should be less complex. It needs to be something that is more easily deployed and can stand alone on its own. And we got into this a little bit in 5.1, but the home area network, shown as the premise network on this diagram, is something that has to be, again, highly interoperable, driven by standards, because there's going to be so many disparate endpoints that will need to integrate into that. And so it can't really be highly fixed or proprietary. So as with any engineering effort, you really have to try and drive out what the requirements are. The requirements are informed by your use cases. Now, in my experience, there are four main operational areas that use cases take place for communications. I'm going to kind of just run through them. It'll smack a little bit of reading the slide, but I hope to provide at least some context for each. The first is a back office system. These are really the traditional networks that are seen within an IT framework, where you're basically doing informational systems, that are for employee support. What are the applications on your computers, maybe your phone circuits that are all helping inform and automate business processes that help run the day-to-day business operations. So then you get into customer networks. Customer networks as a use case would be newer. That would tie into that home area network domain. But it's not just customer in the sense of at the customer home. There's also customer facing network applications. The most prevalent of which might be, say, even your utility website. So, how is your website hosted in such a way that it's highly available for your customers? And then, what information are you displaying to the customers? And how does that tie into your customer information system? How is a customer able to access their own records, and with what granularity? And these are the communication use cases that you have to think about, the different technologies that make things highly interoperable and highly available, such that customers can actually get access to the data that they need, their own data management system, if you will, to enable empowerment over their own energy usage. The third that's listed here would be safety. And there's lots of talk right now in the United States about how we're going to try and create a nationwide emergency response network. So safety in this sense is tied to that. It's first responder. And how is the utility a first responder in a case of storm or in the case of um, natural disaster or any other significant public safety event? Energy being basically a critical infrastructure service, you might see that there are networks that the utility is responsible for that are tied to both the safety of their own personnel in terms of working on the electric system for outage restoration, but then maybe even safety of the general population in trying to get critical infrastructure back up and running that needs the energy supplied by the electric system in order to get it going again. And then lastly, but not least importantly, of course, would be the operational networks. So that ties into so many of the applications that we were talking about in 5.1, because these networks help support all the applications that are really responsible for remotely monitoring and controlling the energy delivery system. And so how these use cases are really come to drive communication networks design, of course, is tied to their criticality and their operational requirements. So some of these might be suited for network topologies that require a little less availability, a little less cost. They might leverage third-party suppliers, and then others that are attributed to be more core to what the utility needs are might be handled in a different manner. And I'm being a little bit vague on this because, in my experience, it does vary from utility to utility as far as how they treat these use cases and how they actually architect the communication networks that supply the data that enable these use case systems to actually work. So tied to those use cases, of course, as I was alluding to, is the different ways that the utility might strategize how they want to deliver on them from a network perspective. At this point, I guess I kind of have to almost downplay my role a little bit, because you start to realize that, within the utility itself, the core product is energy. You're delivering gas or electricity to consumers. Networks are an enabler of how you do that. But if a network wasn't necessary to do it, the thing to recognize is that the utility in this case is not a communications medium supplier. And so, as such, it's really not considered core to the utility to be a communications network provider. As such, there are certain use cases where it makes sense to go to a company that is their core business. That is what they do day in, day out. That is what they know. That's what they understand. It's what they're funded for. It's how they have built their whole business case around. And so that would be basically a public network. Now, the trade offs of a public network, of course, is that you're tied to the service levels, the service response times, the outage response times, um, maybe even traffic prioritization on that network. How do they treat customers? Do they treat certain customers as less important or more important? You run into all of that, and it becomes much more of a you building a relationship with that carrier, managing it through contract, managing it through service level agreements. But the benefit of it, depending on the use case, of course, is that it's it can be less expensive. It can also position you much more effectively for technology refresh, because again, you're handing the reins over to a company that it's their goal to stay on the cutting edge, just driven by technological innovation and consumer demand. With certain of these use cases, though, that's not going to really fly. There are some use cases that are so core to a utility's day in and day out business that it's intertwined to what the real product is, which is energy and optimization of energy. And so that's when the utility actually gets into owning and operating their own networks. In Avista's case, we've pretty clearly lined out that for operational and safety use cases, it must be utility owned and operated. For back office and customer facing networks, it's a mixture of utility owned and carrier owned. And actually, in the references slide, I'm going to point you to a webinar that I was a participant on, one of three panelists, where we kind of got into this whole discussion around whether or not the utility of today needed to get into communications as a core competency, or if it could look to the communication utilities that are available to do that function for them. And so it's a kind of a discussion around private networks, public networks, or hybridization of the two within a utility framework. And so I'm going to actually require that you go out and look at the analysis of that, and that's really going to help fuel some of our discussion on the discussion board. At this point, we really have a gross simplification of networking technologies, breaking it down into two different transport domains, one being wired, one being wireless. Within wired, of course, there's the fiber optic media, and then there's more traditional copper media. Within wireless, there would be licensed and unlicensed and satellite options. Each one of them are used for different purposes Um, and it just really is tied to whatever particular domain we're going to be in. On top of transport, of course, there's all sorts of other considerations. You can have highly proprietary, non interoperable protocols that are transported on any of these domains from a physical infrastructure perspective, or you can have things that are highly interoperable. The protocols can be open standard, they can be proprietary, they can be tied to particular vendors, particular applications. Each one of these must be taken into consideration, and at that point you're really asking yourself, well, what is it that we're trying to achieve? If we're looking for a single source solution that is best delivered by a particular vendor, and they've architected it in such a way that they have a soup to nuts solution, then that's going to point us maybe to something that's a bit more proprietary and fixed to whatever transport domain that they might have had. Say they might have a wireless network transport because their devices all have wireless controllers and they're all speaking on some sort of proprietary RF protocol that no other vendor works with, but is highly groomed, highly tailored to their solution. If you're finding yourself in a mode though, and again, I point you back to that NIST framework where you start looking at which one of those information network clouds are interconnecting with a number of different domains. Well, that in and of itself kind of points you to the fact that a single vendor is not going to suffice. You're going to have to pick something in the protocol layer that is going to speak to the largest number of operators possible. And so then that starts getting into something that is a much more standards driven protocol and is more likely going to be supported on all of these transport types. And so then you have a whole other considerations that you have to look into, like what is your access to infrastructure that you could place wire upon? Wire being a costly but highly reliable, very dedicated transport technology. Um, and then in terms of your growth characteristics, especially as you start getting into fiber optic cable, your ability to grow your technology by keeping your transport basically fixed and in place is greatly enhanced. Depending on the size of your service territory, though, you may find that it's just not cost effective to be able to lay wired communication transport everywhere that you need to connect to endpoints. In which case, then you're going to go into wireless. Wireless is going to be driven by what your access to basically line of sight locations would be. Do you have space on mountaintops that you can procure? Are you in a domain where the topology is such that it's rather flat and it will require you to erect huge towers? Is your coverage area so large that you can't effectively actually get a coverage map over your entire infrastructure, to which you might want to take a look at, well, what is the highest tower that you could possibly build? And there isn't anything higher really than a low orbiting satellite. So in which case then you might look at that as an option. There's really a lot of benefits versus costs that have to be weighed at each. And so it's really tied to your use. What you see on this slide is really one of many different possibilities for a network architecture for smart grid. This particular one is very close to what we have implemented at Avista for our smart grid investment grant and smart grid demonstration projects. The reference at the bottom of the slide comes from Tropos. Tropos is a communications manufacturer that we've partnered with really in terms of building out the field area network. Now they term it the distribution area network on this slide, but that is not in line with what NIST has chosen to name it. But in this example, you can see that there's a number of different wired and wireless technologies. You basically have the utility core systems on the right-hand side of the diagram. That would be represented mainly by your control centers, your backup control centers, your remote offices, any place where the data is both stored or displayed to be acted upon. And then they have basically a connection from those systems, which are aggregations, if you will, and so they're considered, less numerous, and therefore it's more economical for us to make them dedicated wired transport, typically fiber optic. Those will all get to a number of wireless takeout points that are all speaking on basically interoperable protocols that will then get into the home area network, the meter network, the distribution system, and the different control devices that will be present on the distribution system that a distribution management system would need to speak to, as well as anything that might be feeding into other specific modules within an energy management system or the distribution management system. And so a little bit about some of the acronyms, depending on what your familiarity might be with these, but you can see that in the home area network, that's represented by something called Zigbee. Zigbee is a protocol that is just emerging, that is low power. It's very idle, and so it only really transmits when it needs to. Thus, it conserves a lot of energy. So it's well suited for short-range devices, such as those things that would all be within a home, and things that might not have power sources directly, that might need to be powered by battery, for instance. And then there's the meter that's represented by AMI. AMI is an acronym that stands for Advanced Metering Infrastructure. In this case, it shows that it's a 900 megahertz system. There are ANSI protocols that typically metering manufacturers will use. Those, again, are standard protocols. But because of the security concerns, that most of it is encrypted in such a way that really you don't have interoperability of vendor meters. You really have to almost have your meter data management system, which would be represented within the utility core, something that would speak directly to the meters, and tunneling from the meter to the cloud on the right, all the way through the different transport links. And so even though it's passing through all those transport methods, it really looks like as if it was just connected directly to it. And so that's where we start getting into this dance a little bit of how interoperability is great because everyone has access to information, but then that leads to a security concern. So how do you mitigate what the potential risks of having open exposed information is, and when does security concerns trump interoperability advantages? Then some of the other things that we see here are the PTMP, that stands for a point to multipoint. That's basically a wireless technology that's well suited for when you have a very high point of presence, as represented in this diagram by the tower, because it needs to see every point that it's trying to communicate to, as opposed to, say, the center core here, where you see that all a device would necessarily need to see is their neighbor. That is considered a mesh topology because you route yourself through the mesh to get to wherever you need to go by seeing one of your adjacent neighbors. So that's a little bit about this potential network architecture, but I'm sure that there are others out there, and we can get into a discussion of those. So, as we alluded to, there's this great advantage to be had as more and more of the domains can share information with one another. We have a couple diagrams that are lifted right from the NIST framework again that show the core actors and then the need for secure communication flows between the actors in the domains such that the information is available for them to be acted on. And so it all has to be understood, but then how do you also protect against people that shouldn't have, or other parties that shouldn't have access to that information from gaining it? So it presents some security concerns. Now, by and large, you'll see, if you care to crack into the NIST document, that everyone has basically allowed themselves to accept that IP is going to be the standard of interoperability as far as the exchange, the free and easy exchange of information. But you don't have to read very many Wired.com articles before you realize that IP can also be a highly insecure protocol if it's not mitigated against. And mitigation from a security perspective is really what we'll discuss next. So as I've gone around to various utility conferences and smart grid conferences, talked to peers within the industry, you start to see that there's really three basic ways that network security can be approached. But more and more, we're all morphing to the third. So I'll walk through those in some progression. The first might have been a security by obscurity approach, where networks were built, highly proprietary, not a lot of interconnection. You might have control network built upon control network built upon control network, and nothing is exchanging information with one another. The circuits are all point to point. It's a very hub and spoke relationship, and it's usually using a fairly antiquated communications method. We actually have some of those systems still in place at Avista, but are migrating away from them just because of the demands of technology. The second approach might be taking a look at network security really as a technical problem, therefore it has a technical solution. So it might just be as simple as throwing some encryption dongles on a circuit, or changing a password, or doing some sort of security control, but it's really a technical approach. And then we kind of get into where information systems security has been for some time, and utility information security is getting to. And this is really what this diagram is trying to represent. Is if you look at the NIST IR 7628 document, which was so many pages that I really couldn't make it a required reading, but if you wanted to dig into it and become well versed in smart grid security, you would absolutely have to read through that. The 7628 document was heavily lifted from a NIST security framework that existed, previously, the 800-53, which is referenced in step 2 of this process. But you'll see that NIST has created a whole framework for information security that's in place for quite a while. And what strikes you about a diagram like this is it's not technical, and it's not obscure in the sense of not being understood, though a case could be made that it's obscure in its kind of generic description of things. But the thing that you really draw out of it, and what this third approach is its process. It's process driven. So information security is really about continually analyzing the vulnerabilities of your system. You categorize the traffic, you categorize the risks, you categorize the incident vulnerability and what the impacts of a particular incident might be. And so as you get into these high risk, high probability, high impact scenarios, then you start getting into the next step where you're selecting what would be the technical controls, what would be the process controls, what would be your responses to particular incidents, and you set them up in place, you document them well, you implement them, but then you have to continually reassess, you have to monitor, then your monitoring can lead you back into the whole cycle where it really is never ending. I would argue that there has to be an arrow between step 8 and step 1, because you'll recategorize based on what you are seeing in your existing system. So again, like I said, the NIST IR 7628 document is listed in the references section and is a critical component of how smart grid security is being implemented, and it is all being driven by process. It's being driven by assessment and application of mitigating controls to minimize exposure, risk, and impact. So here's your references and required reading. As I just got through, there's the NIST IR 7628. As promised, I wasn't going to make you read the entire thing. However, there is an introduction that's available on the web, and I'd like you to read that. The actual NIST IR is 3 volumes and would probably take you an entire weekend to get through. But this introduction is much less detailed, but provides a good overview into some of the process guidelines that are necessary for cybersecurity within the smart grid domain. And as you can imagine, things you probably read in the press and on the blogs and whatnot, it is a heightened area of concern as we're emerging into the customer domain with automation technologies. Then, of course, I have listed here the framework and roadmap. That is something that we talked about in 5.1. 5.2, it's a diagram that you've seen on many slides, portions of which are really key to understanding the information flows and the need to secure the information flows and how it integrates to the delivery of energy. But that's just a reference for the presentation. It's not a required reading. And then I think I made it aware on another slide here, but I really want you to get into a webinar that talked about the different type of network communications that are available to a utility and which ones make sense for which purpose. However, I didn't get into describing the communication requirements for those use cases. You'll harken back to slide 5 where I said, there's back office systems, there's safety systems, operational systems, and customer facing systems. But what are the specific, say, bandwidth requirements, latency requirements, availability requirements, and when do they mesh or not mesh well with the public or private options that are available? And so what I'm pointing out here is there's actually a response to the National Broadband Plan. They put out a request for information where the FCC is tasked with trying to govern the spectrum, the wireless spectrum in the United States, and they're trying to allocate it as efficiently and effectively as possible. And they put out this request because they're being told by some of their stakeholders that utilities don't need special allowances for smart grid or automation systems in the wireless domain because there are already wireless carriers. And so you can kind of see that this is getting into a public versus private debate. And so when they put this RFI out, they're really just seeking some comment on what utilities saw as necessary or unnecessary, tied to the automation systems. So as part of that request, Avista actually formulated a response. I was responsible for that, and I think it would be useful for all of you to at least get kind of an insight into how I guide my group, and some of the conclusions that we've come to in terms of mapping the use cases to the network types. And so if you could read that, that's the third required reading, and that should really basically summarize the point of this presentation and guide us into hopefully a very invigorating conversation on the discussion boards. Thanks.